So, friends, we will continue with the discussion on module 1. This lecture will be lecture 9, where we will solve another example problem of a frame. Before that, let us add slightly more discussions to the last problem what we solved in the previous lecture. The last problem what we had is an example 1 of a 2 span continuous beam as you see in the screen. Theta 1, theta 2 are unrestrained degrees of freedom marked in green color. Theta 3, delta 4, 5 and 6 are restrained degrees of freedom marked in red color. Keeping fixed beam as a basic module, span AB will have degrees of freedom labels as theta 3, theta 1, delta 4 and delta 5, taking A as the jth end and B as the kth end. Similarly, span BC will have degrees of freedom theta 1, theta 2, delta 5 and delta 6. Bth will be the jth end and C will be the kth end. Taking this as a module, we have generated for example 3, 1, 4, 5, 3, 1, 4, 5, we have generated the stiffness matrix. Similarly, for KBC 1, 2, 5, 6, 1, 2, 5, 6 generated. We partitioned the matrix and got KUU as 2 by 2 and we picked up KUU, found out KU inverse and applied the joint loads, computed the joint load vector, partition the matrix for unrestrained, restrained and unrestrained vector is picked up. Then we solved this for delta u, then we applied and found out the moments, end moments and shears in both the spans AB and BC, and we have the results here. AB is this value and BC is this value. Anyway, from the free body diagram we checked and showed that the values what you have in A and BC are matching what we had. There is another way of checking this which we will now discuss. So, this was the solution we had. Now, we want to check this once again. If you look at the matrix, the K matrix, we said that K has got sub matrices KUU, KUR, KRU, KRR, which we have partitioned the matrix. So, this is unrestrained, restrained, unrestrained, restrained. So, we can also say KRU multiplied by delta U minus JLR will be actually equal to the restraint vector R. So, you can see this is going to be a 4 by 2 matrix. If you look at the full stiffness matrix of size, the full stiffness matrix will be of size 6 by 6. So, this will be 4 by 2, this will be 2 by 1, this again JLR, if you see the vector, this is going to be 4 by 1, okay. It is going to be 4 by 1 and I will get ultimately 4 by 1 as my result. So, from the given matrix KAB, from the given matrix KAB and KBC can always pick up the labels for KRU. So, let us write down this value as the K matrix will have labels 1, 2, 3, 4, 5, 6. Similarly, 1, 2, 3, 4, 5 and 6. So, I have a partition of 2 by 2 because that is my unrestrained degree of freedom. So, now These values can be picked up from the respective K matrices K A B and K B C, and these can be filled up. So, I leave this exercise to you. So, I fill up this matrix and I get K R U matrix 4 by 2 as below, which is going to be E I of, this is first row, first column, second column R. So, it is going to be 3, 4, 5 and 6. So, this value is 0.667, this value is 0.667, and this value is going to be minus 0.667 plus 0.24, which will be minus 0.427, and this is minus 0.24. So, this will be 0, this will be 0.24, this is minus 0.24. So, that is going to be my K R U matrix. Delta U we already have, I am rewriting it again 1.546 E I. So, we have this value here, delta U, which is 1.546 E I, 0.8 minus 0.4 and so on, and I get delta U as this value. Okay. Let us rewrite it here, minus 18 and 57.325, that is what the value we have here. Okay. 1.546 common, 18 and 3.25. So, that is what we are having here. Now, if you look at the JLR vector, this is what I am looking at, JLR, I can write it here, JLR is going to be minus 15, minus 30, minus 50 and minus 20. Let me rewrite this matrix back again here, JLR is going to be minus 15, minus 30, minus 50 and minus 20. Let us substitute in the equation to get RR, which is the restraint vector of 4 by 1, which actually will be equal to, if you look at the original problem, the restraint degrees of freedom are theta 3 delta 4, the restraint degrees are theta 3, delta 4, delta 5 and delta 6. Correspondingly, the reactions will be M3, V4, V5 and V6. Okay. So, let us go back here and do that, which will be M3, V4, V5, V6, which can be obtained as EI times of JLR. So, 0.667, 0, 0.667, that is my KRU, minus 0.427, 0.24, minus 0.24, minus 0.24 multiplied by 1 by EI minus 18 by 1.546, 57.325 by 1.546, and subtract this with my JLR, which is minus 15, minus 30, minus 50 and minus 20. If I do the simplification, I get M3, V4, V5 and V6 as 7.234, 22.234, 63.871 and 13.895. So, let us compare the results what we have with this here. So, I can say the M3, V4, V5 and V6 will be essentially this value 7.234 and this value 22.234 and this value which is 63.871 and this value which is 13.895. So, if you compare this value with what we have here, is exactly the same. So, one can check the solution by this method also, so that the solution obtained by the previous steps and the final step are compared and verified. Having said this, let us move on to the second example problem to solve a single bay single story frame. So, let us take example 2. A single bay single story frame and try to solve this problem. So, let both the ends be fixed. Let us also put the restraint here. Let us apply a loading to this part of the frame which is going to be 12 kilonewton per meter. Let us apply a point load here which is at the center of intensity 50 kilonewton. Let us put 2 point loads here of intensity 20 kilonewton and 30 kilonewton of equal space. Let the dimensions of the frame be height of 6 meters and width of 4 meters. Let us have EI constant throughout. Okay. Now, the first step, as you see, will be to mark the degrees of freedom. So, first let us mark unrestrained degree, then restrained degree. Unrestrained degree we will use green color. So, there will be rotation here which is theta 1, there can be rotation here which is theta 2. These are the two unrestrained degrees what we have, and the restrained degrees are going to be theta 3, delta 4, delta 5 and no axial deformation, therefore, delta 5, theta 6, delta 7 and delta 8, no axial deformation, therefore, delta 8 and delta 9 and delta 9. So, we have following information from this. The stiffness matrix of the complete frame A, B, C, D, that is, this is A, this is B, this is C, this is D, will be of size 9 by 9. Theta 1 and theta 2 are unrestrained degrees, and theta 3, delta 4, delta 5, theta 6, delta 7, delta 8 and delta 9 are restrained degrees. Therefore, the matrix will have a partition. The size of the matrix will be unrestrained and restrained. This is unrestrained, restrained, unrestrained, restrained. This will be 2 by 2. The total size is 9 by 9. Therefore, this is going to be 2 rows and 7 columns, that is KUU, this is KUR, this is KRU, which will be 5 rows and 2 columns, KRR will be 5 rows and 5 columns. So, we have to invert only a 2 by 2 matrix for this problem, that is number 1. Let us also write another statement from this figure. Let us talk about the member. Let us say what is my jth end and kth end, which is the orientation of the member, and what are the degrees of freedom labels. Let us talk about member AB. So, I am writing this as member BA. Okay. So, jth end is at B, kth end is at A. So, this becomes my orientation. So, this is my XMI, this is my YMI for this member. So, degrees of labels could be theta 1, theta 3, delta 9 and delta 4. Similarly, member BC, B end is J and C end is K. Degrees of freedom are going to be, let us say this is XMI, this is YMI for this member BC. So, the degrees of freedom labels are going to be theta 1, theta 2, delta 5 and delta 8. Similarly, for the member CD, C is the jth end, D is the kth end. So, I am going to mark this again as XMI and YMI. Therefore, labels are going to be theta 2, theta 6, delta 9, delta 7. Okay. Having said this, let us mark the displacement vector, rotational and translational both, which is going to be, this is going to be 7 by 2 and this is going to be 7 by 7, total is 9. Okay. So, this is going to be a vector of 9 by 1, which will have theta 1, theta 2, then theta 3, delta 4, delta 5, 6, 7, 8 and 9, where I am going to do a partition at this level. So, this is also written as delta U and delta R. Okay. Also, for the member AB, let us try to find this 4 EI by L value. We need the rotational constants, which is going to be 4 EI. Let us take the EI value for this member is 2I, this member is I and this member is 2I. Let us not take EI as constant, let us vary the EI. Okay. So, in that case twice by L is 4 meters, which will give me 1.333 EI. Similarly, 2 EI by L for the same beam will be 2 EI into 2 by 6, which is 0.667 EI. For the member BC, 4 EI by L could be 4 EI into 1 by 4, which is EI. 2 EI by L could be 2 EI into 1 by 4, which is 0.5 EI. For the member CD, 4 EI by L could be 4 EI into 2 by 6, which is 1.333 EI. Then 2 EI by L will be 2 EI into 2 by 6, which is 0.667 EI.